Monday we're gonna have another day of notes. Candy?
24 days of notes are part of the marathon.
How many more days? At least one. At least one. It's just a lot because we're doing like a whole unit. Fifth period. All right. So get out. Pass this back to Kieran. This is where we left off, right? Yes. Does this look familiar? Okay. Let me make sure I'm recording for reals. I am recording for reals. So, what's that? Okay. Oh, yeah. Now you guys can say hi to second period. All right, so this one we're going to work backwards. K for the reaction below has a value of 55 at a certain given temperature. Calculate the number of moles of HBr present in an equilibrium mixture that contains 3 moles of H gas and 0.45 moles of bromine vapor. Step 1 is write your K expression. So we know that K is equal to products over reactants. So concentration of HBr to the what? Second. Over concentration of H2 times the concentration of Br2. Now sub in what we know. They gave us K, which was what? 55. So 55 is going to equal, do I know HBr? No, so that's going to be our what? X. So 55 equals x squared over, and they gave me the other two, over 3 times, what was the other one? 0.45. So, solve for x. Solve for X. Is that Spanish for X?
Yes.
X. Y, zeta. I still know my ABCs, my ABCs. My daughter Jovi calls the ABCs the ABCDs. It's really cute. She never calls it the ABCs, she calls it her ABCDs. So.
She's more precise.
Yeah.
Do kids still watch CDs? That's still a thing.
CDs.
DVDs, CDs.
We have Disney Plus for that. We listen to CDs in the van though. So we'll get like CDs, like books on CD at the library. No, we don't do DVDs. What'd you guys get?
8.62.
8.62. All right, moles. There'd be units on this. There'd be units on that because I'm solving for an individual thing. All right, the magnitude. The magnitude of K can give a quantitative guide to the amounts of products and reactants present at equilibrium. At equilibrium. Very large, so think about this, very large K values would indicate large numbers of what? Yes, Y products. Oh, well, true. But we know that in the K expressions, products are on the top. Very large numbers of products. In reactions that basically go to, if I have a lot of products, my reaction is going to go basically to what? Completion. Basically go to completion. Very small K values indicate large numbers of reactants. Large number of reactants and reactions that hardly proceed at all. This will be very important later, especially small Ks, is going to save your math life. So, excuse you. There sure who that was. All I heard is, this is the reason that you don't have to do quadratic formulas. We'll get to that probably Monday. So get out your color copy that I gave you. Get out your color copy. So we have the diagram at the right represents an equilibrium at a certain temperature. For the reaction, H2 plus I2 is an equilibrium with 2HI, where H2 are pink dots, I2 are green dots, and HI are green pink. What can be said about the equilibrium position in terms of reactants and products? The likely magnitude of K in the extent to which the reaction proceeds. So first of all, what is your first observation as you're looking at this picture?
There's a lot of HI.
The thing that I noticed is that there's a lot of HI. Agreed? The first thing I would notice is that there is a large amount of HI. HI is a what? Or is the what? Yeah, so this says equilibrium. That says that equilibrium is going to be, it lies to the, which way? Right. Or forward. Right or forward. Which means K must be what? Big. K must be big. Oh, shoot, I wrote it on the color one. Not to write it again. Large amount of HI.
Wait, were we not supposed to be doing always?
Huh? That was just for the color.
Oh, I got a copy that it's from this page.
To the right slash forward, so K equals big. There we go. Flip the page. Flip it, flip it, flip it. This next thing's kind of important. So if I'm being completely honest and humble with you, this is something that I did not know until 3 years ago. So, pretty sure this is the last thing I did not know. I know, you didn't know till right now. This can be done for gases too. I always feel like gases should be spelled G-A-S-S-E-S, but I don't think that's right. It's not right. So, partial pressure of a gas can be solved by the following. It can be solved by the mole fraction of A times the total pressure, which would lead you to a question. What's a mole fraction? Yeah. A mole fraction is just a percent. A mole fraction is equal to moles of A over total moles of whatever's in the mixture. I don't think you'll ever have to calculate a mole fraction, but just know if you want the mole fraction of something, it makes sense, right? The moles of the individual thing divided by the total. Yes? Okay. So consider the following equilibrium. What would be the Kp expression? So now we're talking about pressures. Whenever you are writing a Kp expression, you must use parentheses. We don't use brackets. You have to use parentheses. It's super nitpicky. It's kind of cool. At the end of the AP reading, so after we've graded everything, takes 7 days. That last afternoon, we go into our room, and then they go through each question. Come on. Hello. Yes, I do. Oh, yes. What is it? Ooh. Okay. Thanks. Gianni Massaro. What a raffle! Go get it.
We love gambling.
Go get it. Apparently, it's raffle basket number 5.
Did he get passed for
Nah.
that?
You got a ticket every day you went to Officer April this week, and you got the ticket in the drawing?
Yeah.
So, all right. Anyways, where was I? Oh, end of the AP reading. All right, back to, end of the AP reading. I only know what happened on my question, right? So I'm grading maybe one part of question 5. Well, I'm usually grading the whole question, so I'm grading question 5. I have no idea what happened on question 1, 2, 3, 4, 6, or 7. So we get together, and then the question leader for each one presents their question, what they saw, what people missed. It's actually super interesting. So 2 years ago, it was a question about Kp, and they're like, the main thing is we did not award the point for people who put brackets instead of parentheses. So people did all the math correct, and because it was a pressure, and they put brackets and not parentheses, they took the point off. It's super nitpicky, which is funny because we're not nitpicky at all when we're grading. It's like, how can we award points? But this is something that they are willing to die on. So it's the hill they're willing to die on. I'm just telling you. So make sure if it's KP, you use parentheses. That's it. P parentheses. Yes, you got it. So to write a KP for this, it's pretty much the same thing as KC, but with parentheses. So it would be parenthesis, partial pressure of C to the little c, times parenthesis, partial pressure of big D to the lowercase d, over parentheses, partial pressure of big A to little a, times parentheses, partial pressure, big B to little b. And you know what? If you don't put the PP for partial pressure, as long as it's in parentheses, they know it's a gas. So you don't have to write that PP every time. You can just put in parentheses with ATM, you're good. So PP is partial pressure. What'd you win? What'd you win? Ooh, that is a nice hat. It's nice. Anyways, Johnny, I was just saying, whenever it's KP and you're dealing with pressures and equilibrium, you have to use parentheses. Okay. Do not use brackets. You will not get the point on the AP test. What would KP be for 3Fe plus 4H2O is an equilibrium of Fe3O4 plus 4H2. So KP is going to equal what? Parenthesis what? Everybody's wrong. You're going to think back to what we talked about yesterday. Look at Fe3O4.
Solid.
It's a solid. Remember, solids and pure liquids are not part of equilibrium. I put this one on here on purpose, okay? So, solids are not part of equilibrium. So this is going to be a super easy KP to write. It's going to be parentheses H2 to the what? Fourth, over parentheses H2O to the what? To the fourth. So, I know, it's hard not to write brackets. It's hard not to write brackets. So watch out for solids or pure liquids. They are not part of the equilibrium expression. Okay, now when equilibrium has not been established or is in the process of being established, we must use the reaction quotient, or Q. We talked about this yesterday, to determine what extent the reaction has proceeded. The Q expression, as I hinted at yesterday, is the exact same as K. So if I wanted to write Q for this, once again, back to my brackets, it's going to be, I don't know why I did this backwards, big D to the lowercase d, big C to lowercase c, over big A to little a, big B to little b. So it's the same exact thing, but in a different set of circumstances. The only difference between Q and K is that K is when equilibrium has been established, while Q is the same ratio at any other time. Usually before the reaction has started or begun. And we talked about that yesterday. I said usually you're doing Q at the beginning. So if Q, you have to think about this, if Q is greater than K, that means there's too many products. There's too many products in the reaction mixture, and equilibrium is going to shift left / backwards. Because if I have too many products, it's going to shift back to the reactants. If Q is less than K, there's too many reactants. There's too many reactants. In the equilibrium, oh wait, I missed one, sorry. To the reactant side in order to reduce the product to the ratio where, once again, Q wants to equal K. So Q wants to go back to equaling K. If Q is less than K, there's too many reactants, so it will shift to the right / forwards. Because if I have too many reactants, it's going to make more products. Shifts to the right. To the product side in order to increase the product reactant ratio where, once again, Q is equal to K. If Q is equal to K, it's already at what? It's already at equilibrium. It's already at equilibrium. Or, a couple years ago, I came up with this. It's kind of like a deck of cards. In a deck of cards, the queen should be less than the king. Agreed? A queen is worth how many? 12. And a king is worth 13. So that is right. That's how I remember this whole thing. If Q is less than K, it's right. If it's not, if Q is greater than K, it's wrong. But we're not going to write wrong. That shifts which way? Left. Q is less than K, it shifts left. And if Q is equal to K, it is already at equilibrium. So that is how I remember this. If the queen's less than the king, that's right. If the queen is greater than the king, that's wrong, so it shifts left. If Q is equal to K, it is already at equilibrium. Cool? So that's a little fun way to remember it. Flip it when you're ready. I will hydrate. I don't know why I did that. It felt necessary. I'm excited for the pep rally. You guys excited for the pep rally?
It's for
Winter sports.
It's for winter sports. Seniors, that's why they do it for the winter dance. Because not everything's about football.
Whoa. Wow. We have strong opinions. Strong opinions.
Well, sorry, Chad. We all.
All right. What did he say? What's that mean?
We definitely told Melrose we did not.
Like Twitch streamers refer to that chat.
Oh, got it.
It's like, so, like, instead of saying sorry, everybody gets sorry chat.
It's like a fourth person pronoun.
Okay.
Today, Verdian saying chat.
He said it?
Yeah, Verdian said
Well, he said it to mock Gian.
Yeah, I was.
Oh.
Saying it like,
Yeah, it was rough.
All right. Let's keep going.
I was thinking.
In a situation where two reactions occur with a common, what's this blank going to be? Look at the mechanism below. No. The common what? The blanks are not proportional to words. You guys know that by now. Look at step 1, step 2. What do we have? No.
intermediate.
Yes. With a common intermediate. And what is my intermediate in step 1 and 2?
H plus.
HCO3, because it's there and then it's gone. It's possible to write a series of K expressions. So, for stage 1, step 1, K1 would equal concentration of H plus times concentration of HCO3 minus over concentration of H2CO3. I don't know why I changed from step 1 to stage 1, but I did. Stage 2, K2 is going to equal concentration of H plus times the concentration of CO3 2 minus over concentration of HCO3 minus. And my overall K for the overall equals concentration of H plus to what? H to the second times concentration of CO3 2 minus over concentration of H2CO3. Does anybody see it? So look at those. K overall is literally just the blank of K1 and K2. What is the blank? The product. You just multiply K1 and K2 together. Because if you do that, you can see H times H is going to be H plus squared. HCO3 on the top cancels out HCO3 on the bottom. Agreed? Yes? And then that leaves H2CO3 on the bottom and the CO3 on the top. So it's just the product. Cool? So it is the product of K1 and K2. The other weird thing you can do with K is manipulate it. So you can do these little changes to it, and if you change the original, it changes the new thing. So let's write out our original K for this equation. So take a second and write out your K expression for this. Write out your K. What? What happened, Isaac? Well, this doesn't say KP.
But the gases.
I know, but gases can have concentrations. So if it doesn't specifically say KP, you don't have to really use the brackets. So I'm going to use bracket. So I have NO2 to what power? Second over N2O4 to the nothing. All right, if the equation is reversed, my new K would now be, you guys see that I flipped it, yes? It now would be bracket N2O4 over bracket NO2 squared. What did I just do to my original K?
Inverse.
Yes. So the new KC is essentially 1 over KOG. So if I flip it, you take the reciprocal for the new K. If the equation is halved, my new K is going to be bracket NO2 over bracket N2O4 to what power? To the 1/2 power. Yes. So my new KC is the square root of KOG. How else could I write that?
Wait, no, sorry.
To the 1/2 power. I could also say KOG to the 1/2 power. To the 1/2 power. And then lastly, if I double the equation, my new KC is going to be NO2 to the 4th over N2O4 to the 2nd, which is, what did I do to it, Tyler? I heard you say it?
Squared.
It's squared. So my KOG is squared. If it's tripled, my KOG is going to be what? To the 3rd. KOG to the 3rd. So there will be a question in the homework. We're going to have to do that. Just manipulating K. It's helpful to know those things. Flip it when you're ready. Flip it when you're ready. How much time we got left? Pep Assembly's 5th. Perfect. Perfect. Les Chateliers. Principal. Is anybody here in French? You are? All right, say that in your best French.
No way.
I say Chatelier.
Yeah, that's pretty good. Do that again.
You want to pronounce it?
Chatelier.
Yeah, that's very good.
You want to pronounce it?
Les Chateliers.
S.
All right. Les Chateliers principal. I took Spanish, so I'm like, I can't. What? No. This is vital. That's why I already put a bunch of stars there. Les Chandeliers. Les Chat. There, at the full circle. We brought it all the way back. Yes.
If you become a Twitch streamer, you should have your like username be a Chatelier.
Oh my gosh. Yeah. I bet someone's already thought of that. I'm sure. No? That's true.
Bubbles overlap there.
I can't wait till I have that spare time to be a streamer. Probably once my daughters are out of high school.
Lab streams?
I just stream chem notes. Stream chem notes. Oh, like a lab stream.
I would watch Mr. Heller.
Okay.
Watch Heller go study into a
I am becoming.
Yeah. All right, bring it back in. Bring it back in. Le Chatelier's principle states when a stress is placed on a system at equilibrium, No. This is for you. When a stress is placed on you, what do you try to do with the stress? What should you do with it? Get rid of it. Eat a lot of food. Hopefully, the answer is not push it back down. All right? Because release it violently at your friends. Okay. So, you have to, in chemistry, you can't do that. Something has to change. So, the stress is placed on the system, there will be a shift in the position of the equilibrium to reduce that stress. So, the shift occurs because the stress will cause Q to change. And the equilibrium, we talked about this, has to shift back to Q, bringing it into numerical agreement with K. So there are 3 types of stresses we're going to talk about. And I promise you I didn't give you enough room to write, because I can barely fit what I'm about to write. So write small. Stress 1, we've talked about a little bit. Addition or removal of products or reactants. So, part A, right? It will shift to the other side if something is added. So if something's added to the reactant side, it shifts to the right. Something's added to the product side, it shifts back to the reactants, it shifts left. Part B, you have to think about just a little bit more. If something is removed, which way will it shift? Yes, it will shift to the side it was removed from. It was removed from. I think about this kind of like diffusion, like of water. So if you have like a little hole, right, in the middle, and I add water to one side, it's going to push it to the other side, yes? If I remove water from one side, it's going to go back to that side that I removed it from. Do you guys see what I'm saying? Yeah. Okay. So that's the first way you can change it. The second way, go for it. There's an electric sharpener.
Just can't take notes anymore.
Videos in first period.
Is that all that we're writing for?
Yeah, that's all for one.
False alarm on the small writing.
Well, I mostly write like a third grader, so maybe that was more for me than you guys. A change, sorry, maybe you don't have to write that small. The next one is a change in pressure. And then I put volume, right? Because if I change the pressure, it would change the volume. Or if I change the volume, it could change the pressure. Boyle's law, right?
Yeah.
Okay. So when pressure is added, it will shift. It will shift to the side with the least number of moles of gas. It'll shift to the side with the least number of moles of gas. That makes sense, right?
Yes.
Because gas is a fluid, and fluids do what? Flow. Fluids flow. So if I wrote a little equation here, if I said 2C solid, so I've got some solid carbon, plus O2 gas is in equilibrium with 2CO gas. If I add pressure to that situation, which way will it shift? It will shift left. It will shift left. Why? Well, the left side has how many moles of gas? 1. The right side has how many moles of gas? 2. I should have put a parenthesis around that. The other thing I could do would be, what if I increase the volume? If I increase the volume, what does that mean I'm doing to the pressure? That means I'm lowering the pressure, agreed? Yes? That means I'm lowering the pressure, which means it will shift which way? Shifts to the right. It'll shift to the right. Because if I remove pressure, it's going to shift to the side with the most moles of gas. Yes?
Will it shift at like the proportional rate?
Yes.
So like if you double the amount of pressure, then the amount of the rate of will double.
Yeah, just like our graphs that we did. Yeah, you got it. The last one, and this is the one that has the most writing. Did you guys fit it on that one? Yes. Is a change in temperature. So, if exothermic, what is the sign for an exothermic reaction? Negative. Add heat, put heat in quotations because you're literally going to write the word heat as a product. Add heat as a product. Period. If endothermic, what is the sign for endothermic? Positive. If it's endothermic, we're going to add heat, put that in quotes, as a reactant. Add heat as a reactant. Now we're going to write a little equation out. So I've got 2 FeCl3 plus 3 CaOH2 is in equilibrium with 2 Fe.
What's
Okay. CaOH2 is in equilibrium with 2 FeOH3 plus 3 CaCl2. And I would tell you that this equation releases negative 36.3 kilojoules of heat per mole. So if you saw an equation like this, and I literally just came up with this idea last year, and it really helped. So I'm getting better every year. I want you to physically write in your products plus heat. Write plus heat. So literally write plus heat as a product. That will really help you with your shifts. So you know that heat is a product. Because once heat's a product, now it's just like number one. So on this equation, if I would add FeCl3, which way would it shift? No.
Right.
If I add reactant, it's going to shift to the products. That means a shift to the right. If I would remove, I don't know, CaOH2, which way would it shift? I'm removing something from the left, so it's going to shift back to the left. It shifts back to the side you remove it from. It's going to shift to the left. If I increase the temperature, which way is it going to shift? Left, because temperature is a what? It's a product. So it's really helpful to write out temperature as a reactant or a product. So if I increase the temperature, I'm adding a product, so it's going to shift back to the left. Yes?
So you can think about it as if you increase temperature, your pressure is also going to go up, and if you add pressure, you shift.
You could do that too. Yeah. But do it like this, because you don't want to start thinking about two different variables at once. Note, catalyst cause no change in Q or K, so they do not affect the equilibrium. So you know there's going to be some kind of question out there. Like this would be a good multiple choice question on the AP test. Here's your situation. A catalyst is added. Does Q become less than K, greater than K, equal to K, or no change? Like I can see that being a question. No change.
Even if the catalyst is a reactant.
A catalyst wouldn't be a reactant. You're not going to add a catalyst that's going to react. Has to not react. It can't change, right? It does not change what's going on in the equation. Increasing the total pressure by adding an inert gas, this is super important. If something is inert, what does that mean? It doesn't react. That will have no effect on the partial pressures of gases. Therefore, no effect on the equilibrium. No effect on the equilibrium. So, if an inert gas is added, it doesn't change anything. It doesn't react. It doesn't change your equilibrium. And then down here, there's a big old table I found with a bunch of examples. So on this one, the only thing I would do, would you write heat as a reactant or a product on this one?
You would write it as a product.
Yes. So plus heat. And that gives you a bunch of examples of what would happen. So Monday, we will review this. You can see what's on the next page. We'll do a quick review. Then we're going to go into KSP, another K. So we have KC, we have KP. Monday we're going to talk about KSP.